All right, so we are done with quizzes for a while, I think. Break from quizzes. Not that I've completely ruled them out for in-class in the future. I think perhaps more likely they might be online instead. But maybe once in a while we'll have an in-class quiz. But we will still take breaks. You know, with a 70-minute class, it gets kind of long. So about 35 minutes into it, about 11:45, take about a 3-minute break. If you need to use the restroom or get a drink or whatever, just stretch, stand up and stretch, we'll do that. And then about 11:48 or so, then we'll do the last 32 minutes of class or so, typically, is what I'll be aiming for. Here are the lectures for today. Lecture A today, more of what we've done recently, including improper integrals, comparison tests, probability. We have talked about PDFs, probability density functions. I also want to introduce something called the CDF, Cumulative Distribution Function, that they're very much related to each other, and there are two different ways about thinking about probability and its relationship to calculus. That's probably so much stuff that we can't fit it all into Lecture A, so there'll be some Lecture A spillover into Lecture B. And then I want to start Chapter 8, which we get into more physics kinds of things, starting with geometry, areas, and volumes by slicing, which with the areas you should have done before. I want to let you know that on Thursday, there's a person from the company called Allianz. Okay, I think that's how you pronounce it. It's not Allianz, it's Allianz. They're an insurance and investment company. Annuities is what they sell. And they have actuaries and other quantitatively oriented people who work for them. And so if you're interested in being an actuary, the person or persons coming on Thursday will be talking about what it's like to be an actuary, and in particular an actuary at Allianz, and you can get their names and get some contacts and maybe find out about possibilities for internships or something. Being an actuary is definitely very dependent on being good at math. They have a lot of tests they take, and a lot of the tests are very much math focused and applying math, especially probability and some financial math to problems in insurance, where you're trying to assess risks. You know, how much money should we charge our customers so that we can cover them if they have a loss, if their house burns down, for example. Bad things can happen once in a while to people, so you buy insurance to try to cover those losses, and when they get lots of customers, they can figure out based on past data what kinds of rates they should set their premiums at, so that they can make money, but at the same time they can still cover their customers. So if you're interested, 3 to 4 o'clock on Thursday, probably in CC 230, though that's not absolutely confirmed. I'll get back to you with an email. All right. So we've talked about probability. And improper integrals. Let me do an example. And this is going to be kind of a general example. Actually, it's going to be a couple examples. The white will show up here. There we go. That are also related to the comparison test for improper integrals. I want to consider functions of the form some constant over x to a power. Some constant over x to a power, positive power. X is going to need to be bigger than 0 here, and p is also going to be bigger than 0. And I'm wondering, over the interval from 1 to infinity, not 0 to infinity, but 1 to infinity, what values of p will lead to an improper integral that's going to converge? And if it does converge, will it be a probability density function? Will the area from 1 to infinity equal 1? Well, probably not. Probably if it's going to be an area equal to 1, c is going to have to depend on p. It's not just going to be any old constant up there. Let's go ahead and calculate the improper integral. C over x to the p. Something you should have read about. It's a limit as b goes to infinity of the integral from 1 to b of the same function, which I'm now going to write as c times x to the negative b to make it more clear how to integrate it. And we're actually going to have two cases here initially, and it's actually going to split into more cases after the initial splitting. If p is not equal to 1, is different than the case where p does equal 1. Why? What happens when p is 1? You get a natural log function involved. If p is 1, you're really integrating c over x. That's going to be c times the natural log of x. I don't need the opposite value signs, though I can put them in. It doesn't hurt, since x is positive here. It doesn't hurt to put them in, but I don't have to since x is positive. So c times natural log of x. What about when p is not 1? Then you got to add 1 to that exponent and divide by the same number. Oh, I forgot my limit sign. Okay, sorry. Limit as b goes to infinity of c times natural log of x. And I'm evaluating from 1 to b. A limit up here as well. Limit as b goes to infinity. c x to the careful negative p plus 1 over negative p plus 1. Which I can also write as 1 minus p, by the way, right? Negative p plus 1 would be the same as 1 minus p. Does this limit exist here? What do you know about the natural log function? It does grow in a concave down way. Does it have a horizontal asymptote? It does not, even though it's growing pretty slowly. It does not have a horizontal asymptote. This limit does not exist. Some people might say it equals infinity. It would be okay to write that in this case, but don't take that to mean that infinity is a number for us. It's not. I guess I'll go ahead and say e equals infinity, but take that equal sign with sort of a grain of salt. It's not saying that infinity is a number. It's just saying this quantity is getting arbitrarily large. Technically speaking, I'm plugging in x equals b. X equals 1 gives you natural log of 1, which is 0. This thing here, without the limit sign, equals c natural log of b. But the limit of the whole thing is what equals infinity, quote unquote. What about this? Does that limit exist or not? It depends on what p is. Can you tell just by looking at it? Can you think it through? Maybe I should, oops, I need to evaluate this from 1 to b as well. Maybe I should plug in b here. And maybe it would be helpful to put the b to this power in the bottom, which means I need to negate the power. I could write it like this. A little tricky there. Got the c, I'm plugging in b for x. B to the negative p plus 1 is the same as 1 divided by b to the p minus 1. I still have the 1 minus p down there. I also plug in x equals 1 to get this term. Does that limit exist? It does depend on what p is. What values of p would make that limit exist? Yeah, p is bigger than 1. Because if p is bigger than 1, then I have a positive power of b down there, which is going to make the denominator get bigger. It's going to make the whole fraction get small, go to 0. On the other hand, if p is less than 1, like 0.5, 0.5 minus 1 is negative 0.5. It's a negative power there when p is less than 1, which means I really should have on top with a positive power, and it's going to grow. Okay, it's going to go to infinity as b goes to infinity. So this converges to C over 1 minus P, which can also be written as, negative C over 1 minus P, which can also be written as C over P minus 1, if P is bigger than 1, and it diverges if P is less than 1. We're already assuming P is bigger than 0, so it diverges if P is between 0 and 1. So overall, the overall integral converges when P is bigger than 1 and diverges when P is less than or equal to 1, because it also diverges in the P equals 1 case. It's a common kind of function to use the comparison test with, to know that this integral converges when P is bigger than 1. It's common to do that, and in fact, in one of your problems, you should have done that before you were integrating. It was 1 over u plus u squared. You should have noted that that's less than or equal to 1 over u squared when u is bigger than or equal to 1, and the integral of that one converges. So therefore, the integral of this one converges. One of the comparison test problems for today. By the way, people who came late, you should be turning your homework in. But what about making it a probability density function? Anybody else? In the case where P is bigger than 1, it converges to this. What value of C will make it a PDF? P minus 1. Because then you have P minus 1 over P minus 1 is 1. And you want the area, the total area under your probability density function to equal 1. So this converges if P is bigger than 1, and in that case is a PDF probability density function if C equals P minus 1. So you can use it to model various situations perhaps. And how do you calculate probabilities? You integrate. So if you wanted to find, for example, the probability that some quantity is between 2 and 5, and it really doesn't matter whether I use less thans or less than or equal to's here because of the continuous nature of this variable, though I think I will typically use less than or equal to's. You integrate it from 2 to 5. Whatever the function is, whatever value P you're using, I'm still assuming little p is bigger than 1. This little p is my power, big P, that stands for probability. It's just a shorthand symbol for probability. The probability that x is between 2 and 5 would be the integral of the function from 2 to 5. Maybe p is something specific, maybe it's not. Okay. You should be able to do that for something specific. With this, I can introduce something called a cumulative distribution function. This is called a probability density function. What's the corresponding cumulative distribution function, or CDF? CDF stands for cumulative distribution function. Cumulative, essentially, it's keeping track of probabilities cumulatively, up to and including some point. It helps you find probabilities that your variable is less than or equal to something. And that something I'm going to call a little x. So this bigger x represents my quantity that I'm measuring. Could be a wait time. Could be a length of something after it's full grown. Those are different kinds of examples of random variables, variables that vary in a random way. And I might want to find a probability that I'm less than or equal to some unspecified value here, x. The reason I'm using an x there is because I want this to be a function. Ultimately, a function of this little x. How do you find it? You integrate your PDF. Should probably use another letter for the variable integration. How about a W? over its domain on which it's a PDF from the left-hand endpoint, if there is a left-hand endpoint, to little x. If the left-hand endpoint happens to be minus infinity, which it can be, then it's a minus infinity, and it's really an improper integral in that case. Note, A could be minus infinity, and if it is, it's really an improper integral where the lower, you take a limit as the lower limit goes to minus infinity. For this example, take these functions here. When p is bigger than 1, the a is 1 in that case. That's your PDF. Integrating that gives you probabilities, and we are integrating it. We are getting a probability. But in so doing, we're creating a new function called a CDF. It's going to be an antiderivative of the PDF because I'm forming it by an integral where the variable's in the upper limit of integration. You've seen this before. This is how you construct antiderivatives, but it's a very special antiderivative. It's going to give you the probability that your variable is less than or equal to the given number there. What does this end up equaling here? I'm just going to use a W here, sorry. This is the same as p minus 1 times w to the negative p. So we're going to get p minus 1 w to the negative p plus 1 over negative p plus 1. Evaluated, w goes from 1 to x. Plug in w equals x. You really do want to plug the x in there. Oh, I should simplify before I do, sorry. This does simplify nicely. This cancels with that. Not to leave a 1, but to leave a negative 1. So this really becomes negative w to the 1 minus p when you plug in and simplify, you get 1 minus x to the 1 minus p. This is for x greater than or equal to 1, and p being bigger than 1. Sorry. It gives you probabilities of this type. What's the probability that my wait time is going to be less than or equal to something? Or what's the probability that my thing I'm measuring is the length of when it's full grown, maybe some animal that's always bigger than 1 meter or something in length. What's the probability that my animal when it's full grown is less than or equal to 1.5 or something? It's common to call this capital F of x, to emphasize that it's an antiderivative of the little f. The derivative of capital F, the derivative of the CDF is the PDF. The derivative of the cumulative distribution function is the probability density function. So you want to know that relationship between them. You also want to know how to interpret the graphs. Actually, let's take a look at one of your problems for today that I think was perhaps a little tricky. It was one of your probability problems, one of your 2 probability problems from section 8.7. I'm thinking of this one that has the funny spike in it. Wait, I signed up today. That's supposed to be a PDF. So the graph that you're looking at there looks about like this. It's got a funny spike in it. Could that ever happen? Fraction of students per test score. Evidently, for some strange reason, there was a spike in the number of people who got scores near 50. But the question is, does that imply that most people received scores near 50? The answer was supposed to be no, even though that's where the graph is highest. But it's because the spike is so skinny that even though it's high there, the integral is not very large over this kind of interval. Most people scored down there because it's relatively high and also wide. So you get large areas. You integrate functions, you integrate the PDF like this to find probabilities, to find the fraction in this case of students in different ranges. So again, even though it's a high spike, there were a relatively large number of students who got a score near 50 compared to, say, 60. Most of the students did not score 50 because the area is not super large because of the skinniness of it. That's a PDF. That's a little f of x. What's the corresponding big F of x here? The CDF. It's the integral of the PDF from 0 to x. What would the graph of this look like? This is important. Understand the relationship of these graphs. Well, the integral of this from 0 to 0 is going to be 0. The CDF is going to start at 0. It's going to be an antiderivative of the PDF. Its derivative will be the value of the PDF. The values of the PDFs will be the slopes of this one. So the slope starts out positive and increases. So the graph's going to be concave up. Up until this point where you reach that peak, at that point the graph is going to become concave down. Still going up because the value of the PDF is positive. This always goes up. It's just where is it concave up and where is it concave down? It's concave down now because the value of the derivative is decreasing. So the slope of this is decreasing. Until you get to this minimum point here where the graph becomes concave up again. And in fact, because of the sharp spike right there, it has a relatively high slope for a short amount of time before the slope is concave down. It's decreasing after that point. Something like that is the graph of the CDF. How do you read the graph? How is it useful? For any given, for any given number like 40, for example, it's the value of the graph, not the area, that gives you the probability. This number right here would be the probability of x being less than or equal to 40. More generally, differences give you probabilities. If you want to find the probability that x is between, say, 40 and 60, that number right there is the probability that x is less than or equal to 60. It's the difference of these two, the distance along this line segment, that gives you the difference. Well, it gives you this probability, which is the same, it turns out, as this probability. But that should make sense. After all, this is really f of 60 minus f of 40, which is the same thing I get by integrating the little f from 40 to 60. The integral of the little f from 40 to 60, the area under it from 40 to 60, that area is also going to be this difference right here, which is interpreted as a length on that line segment. So you want to have the flexibility of understanding and thinking about probabilities with either function. And that's something you should have gotten out of the reading somewhat. You're doing section 8.7 especially. And some of your homework questions for Wednesday are going to be related to that. For this function, what do the graphs look like? The graph of that kind of function when p is bigger than 1 looks like this. It's the little f of x. What does the graph of capital F of x look like? It's got to start at 0 because the probability of being less than or equal to 1 here is 0. The data values start at 1 and go up. We're ignoring what happens when x is less than 1. The formula for the function looks like that. What does that graph look like? It's increasing and concave down. It's going to have 1 as a horizontal asymptote, like that. The value of p just affects how steep it is. That's all it does. So that would be what the capital F, the CDF, would look like for this example. How's this related to the comparison test as well? We could consider other kinds of functions as possible probability density functions, like this one. Which brings to another point. I'm integrating this one from 0 to 1, not 1 to infinity here. And it's actually not an improper integral, so that's actually not a good example. Let's consider this example here. That's actually of this form as well for the function, but it's at different limits of integration. 0 to 1 instead of 1 to infinity. Turns out that's an improper integral too. And it turns out to diverge when p is bigger than 1, and converge when p is between 0 and 1. How is it improper? It's because this function has a vertical asymptote at 0. I guess in this case p is 1/2, by the way, because I have a square root of x there, same as x to the 1/2. Let's do the more general case. C over x to the p again. But now I'm integrating from 0 to 1 instead of 1 to infinity. The impropriety, so to speak, is the lower limit of integration, which I'll call a. This is really a limit as a approaches 0 from the right. Same kind of function, different interval. And again, it is improper because when p is bigger than 0, this function's got a vertical asymptote. How do you know the area is finite? It's not necessarily finite. It depends on the value of p. Once again, you can do two big cases, one where p is 1 and one where p is not equal to 1. In the one where p is 1, you once again get natural log, c times natural log of x. X goes from a to 1. In the other case, you get c x to the negative p plus 1 over negative p plus 1 again. Same antiderivative. Got my limit sign again. But it's a different kind of limit. I'm letting the lower limit of the integral go to 0 instead of the upper limit going to infinity. Turns out this limit does not exist. You might say equals infinity. The graph of the natural log function looks like this and goes down to negative infinity, down forever and ever without bound, as x approaches 0 from the right. We'd really be subtracting c natural log of a, and therefore negative c natural log of a would go to plus infinity. It diverges. This one turns out to converge, but not when p is bigger than 1. Instead, when p is between 0 and 1, this one converges. Because in that case, you can write x as a positive power on top. Like if p is 0.5, for example. Negative 0.5 plus 1 is positive 0.5. X to the positive 0.5 goes to 0 as a goes to 0. On the other hand, if p is bigger than 1, like 2, this would be x to the negative 2 plus 1, x to the negative 1. Really 1 over x, which goes to infinity. as when you plug in a as a goes to 0. So it turns out that this converges in the opposite case. This converges if p is between 0 and 1. To what? Plug in 1, you get c over negative p plus 1. Subtract what you get when you plug in a. Although that's going to go to 0. So in reality, this thing converges to c over negative p plus 1, or if you prefer, c over 1 minus p, as a goes to 0 from the right. Back here, this was a PDF if c was p minus 1, which is bigger than 0 when p is bigger than 1. Here it's a PDF when c is equal to 1 minus p. And 1 minus p is bigger than 0 if p is between 0 and 0.5. This is an example like that. P is 1/2. This does converge. The integral can be done. It equals 2. Therefore, to make it a PDF, make the top 1/2. Make C. Something wrong. That integral's 2. Is that supposed to happen? C is 1 there, and P is 1/2. Okay, I do get 1 over 1 minus 1/2. 1 over 1/2 is 2 for the integral. If C were 1/2, P is 1/2 here, that is the same as 1 minus P in this case. So it is working. So you can put a 1/2 at the top, or you can write it like this. That now gives you an integral that converges to 1. And my initial thought with this other example was that I could use the comparison test to prove it converges, but actually it's not an improper integral because it doesn't have the word glass because of x equals 0. So I don't need the comparison test for it. It's not improper. It is interesting. You certainly can use it, modify it to make it a PDF. Its value is that. So if I define the new function this way by putting that quantity, 2 minus, this is a natural log, by the way, of 4, down here, that makes it a PDF now. And I can find the corresponding CDF. Let's do that before we take our break. The corresponding CDF of this I can find by integrating from 0 to x of little f of w dw. Little f of x is this function. Replace x with w, do this integral, and you will get the CDF. And it probably looks like I need to give this function a name for it to see the output. Let me call it capital F of x. Oh, here we go. We saw the output. That function is the CDF. This PDF. Now I know these ideas are difficult, okay? CDF, PDF. Okay, but we're just going to keep coming at them over and over today, here, after our break, a little bit more, as we continue through chapter 8, to help these ideas sink in better. You sort of need to see them over and over again to get them to sink in. Okay, let's take our little break. 3 minutes.